At the end of primary drying, the product looks dry. The ice has been removed and a porous cake remains. But visually dry does not mean completely free of water. Some moisture can still remain associated with the dried matrix. This is where secondary drying begins, with a different objective: removing residual water from the product.
After primary drying, the product is a porous, dried matrix formed by the removal of ice. But within this structure, some water can still remain associated with the solid. This residual moisture may interact with proteins, sugars, polymers, and other formulation components. So although the cake appears dry, its microscopic state can still contain water that influences product behavior. Secondary drying is designed to remove much of this remaining moisture. During secondary drying, residual water gradually becomes more mobile. As product temperature increases, thermal energy helps overcome the interactions holding water within the dried matrix. The molecules become less constrained, move away from the matrix, and eventually enter the vapor phase. This process is called desorption. Unlike primary drying, there is no advancing ice interface here. The ice is already gone. The focus is now on releasing water associated with the dried solid. Desorption is promoted by increasing product temperature. Heat is transferred from the controlled shelf through the vial and into the dried product. But higher temperature does not automatically mean better drying. More thermal energy can accelerate moisture removal, while excessive temperature or exposure can increase product stress. The process therefore has to balance effective desorption with product stability. An important point is that the goal is not necessarily zero moisture. Too much residual water can affect stability, but excessive drying may also be undesirable for some formulations. The appropriate moisture level is therefore formulation dependent. Secondary drying is not about removing as much water as possible. It is about reaching the right moisture state for the product. Why does this remaining water matter? In an amorphous matrix, water can act as a plasticizer and increase molecular mobility. Changes in molecular mobility can influence both physical and chemical stability. But the effect depends strongly on formulation composition. That is why secondary drying conditions must be developed together with the stability requirements of the product. Temperature is a major driver of desorption, but it is not the only factor. Exposure time also matters. Formulation composition and vial configuration can influence how heat reaches the product and how moisture is removed. And once water leaves the product, it must also be transported away from the chamber. Secondary drying is therefore controlled by several interacting process and product variables. These factors come together in the secondary drying cycle. The product temperature is gradually increased during the ramp, followed by a hold period to continue moisture removal. The cycle then transitions into cooling. The exact temperature and hold time are not universal. They are established according to the formulation, product stability, and desired moisture condition. But how do we know secondary drying is complete? Not simply because a certain amount of time has passed. Residual moisture needs to be measured, and the resulting data evaluated against the desired product condition. Product stability and process conditions also provide important evidence. The endpoint is therefore based on product and process evidence, not heating time alone.